This is a spotlight presentation for a paper by Rishit, Sheth and Roni Khardon published in the NIPS Conference 2017. Bayesian predictors based on Bayesian models are optimal when, first, model assumptions are correct, and in addition, one can perform exact inference. But condition 1 is often false, and in most complex models one has to resort to approximate inference, and 2 is also false. The paper explores basic questions in this context. Should we use a Bayesian algorithm or not, and if so, which approximation should we use? We provide quantitative answers as risk bounds. We consider a general supervised or unsupervised prediction problem. On this slide, we show the supervised one when example x and label y are distributed according to an unknown distribution D. The goal is to predict y, and the log loss provides a notion of error. The risk is the expectation of the loss according to D. This is simple to define for a single parameter estimate, W. A Bayesian predictor aggregates the prediction according to its posterior Q of W, and then the loss is defined naturally for its prediction. These definitions can be extended for models with two levels of latent variables, which are the focus of this paper. Our paper gives theorems that bound the risk of posteriors computed by optimizing the so-called collapsed variational lower bound. They show that the risk of the Bayesian predictor, using this posterior, is bounded relative to the risk of the best parameter estimate. We emphasize that this is done without assuming that the Bayesian model is correct and without knowledge of the distribution D. Therefore, the Bayesian algorithm can be seen as an insurance scheme. The model does not need to be correct, yet the error is bounded against any simple predictor based on parameter estimates. This is a technical statement of the result. We need the psi function previously defined by Germain and colleagues. This is a property of the loss function. We also need a second property of the loss function, the largest eigenvalue of its Hessian. With these, we have that the loss of the variational algorithm is bounded by the risk of any simple parameter W hat. The slide hides many details, but the additional terms are shown to decay at the rate of 1 over square root of n. A key observation for our proof is the fact that the variational algorithm performs regularized cumulative loss minimization. The paper shows that the theorem can be applied to complex models, including the correlated topic model, the family of generalized linear models, and the conjugate sparse Gaussian process. Please see the paper for more precise statements and full technical details.